It would be great. I would love to play more D&D.
Hello, welcome to class, everybody.
I prefer Access Now. That's my favorite game that takes me out. I can sit down and
I don't even know what that is. You must really be a nerd.
See, I feel like
Respectfully.
at
I'm not
times
being
I fit in the
disrespectful.
nerd world, and then other times I just feel like I'm not in the nerd world.
you have a foot in each world.
Yeah.
You don't look like a nerd, you don't act like a nerd, but
Yeah.
sometimes the things that come out of your mouth, I'm like, what?
That's exactly how it is. No, if you walk by me in the street, you would not say, "Oh, that guy's."
Yeah, he's a math major.
Yeah,
He's,
you would not say that. You would
No.
never say
Sorry, family bonding.
It's all good. It's all good. All right. The recording's rolling. We're on camera. Take 7. Okay, so Lagrange's theorem. Do you remember what that says without looking at it? Anybody remember? Roughly, just like even in loose terms.
The amount of distinct cosets is the order G divided by the order H.
Yeah, that's pretty good. Let's put that up. That's not bad.
That's
That was really
good.
good, actually. So, yeah, so let's ooh.
That's beautiful.
Oh my God. And this board's all clean. This is really extraordinary. Log, okay, I spelled it right. Okay. Yeah, what a day, indeed. So G is a group, a finite order. This, and H is a subgroup of G, possibly the same. Then as Trinity said, the number of distinct cosets of H and G. So that remember, this is all the cosets. So you have A1H, A2H, and H. Remember that little picture I drew where we took H and then we looked at all the cosets and it just filled up this whole rectangle representing G. So the number of those is equal to the order of G over the order of H. So that's like a great way to say it. But then there's also like this implication here that if you have a subgroup of a group, its order always divides the order of the group. So that's kind of like the meta takeaway in some ways. This is very technical, right? It's like, how the hell do I use that? But so if H is a subgroup of G, then the order of H divides the order of G. And that's going to get us a bunch of stuff. And that stuff starts on the next page. So page 154 for those with pages, page numbers. Next page for those without. Let's see here, what the heck? So corollary 1 is kind of exactly what Trinity said. Corollary 2 is that the order, so if you have an element of a group of finite order, everything here is finite order, then the order of A divides the order of G for every element. So why would that be? Why would that follow from that over there? So if I said the order of A is equal to K, what's another way to think about A in terms of group structures and how it lives inside of G? Semi-suggestive fingers here, just an arbitrary whirling. What's this? Cyclic subgroup generated by A, right? What is its order? It's K. Exactly. So if I take an element of finite order, it generates a subgroup of that same order, a cyclic subgroup. And by Lagrange's theorem, that order, because this is the subgroup, divides the order of G, so the order of the element divides the order of G. So it's kind of just a little bit of a twist of looking at things. Does that make sense? Why that would be true? Cool. So that's a nice, easy one. Let's check out corollary 3. This is a kind of a powerful result that's very quick and easy. So corollary 3 says that every group of prime order, let's just say it's P, is isomorphic. It's so morphic to Z mod P. So this like instantly classifies infinitely many groups. If the group has a prime order, you know it's basically, you can just think of it as Z mod P. So let's think of that. We've got a group of prime order. So what are the order of the elements in G? So let's see here. So order of G is equal to P of prime. Let's take an element A in G. What's the order of A? What are the possibilities? P or P or 1, right? Because P is prime, so it only has 2 factors. So 1 or P. What does this mean about A? What element has order 1? The identity. So this would imply that A is equal to the identity. And that's not going to really get us the whole group. It's just going to be itself. So what's the other possibility? E. So this means that the order of this element A, if it's not the identity, must equal P. And so that generates CP. Does this make sense that if I have an element of order P, and that's basically the only possible order, then my group must look like this: E, A squared, up to A to the P minus 1. And all those powers are going to be distinct because the order of A is P. And this fills up the group. This is actually P different things, and the order of the group is P. So this must encompass everything that's in there. Does that, think about that for a second. If the order of the group is P, and this element produces P distinct things, this must be the group. Right? There can't be anything else. Because you tell me, oh wait, isn't there some element B? And I no, because here's P things and they're all distinct because of this. So B must equal A to the J for some power. How's that feel on Sydney? Do you want to talk about it a little bit?
I think I need like
Okay. So let's say I have a group. It's a little challenging. We'll try this though. So let's say I have a group G that has order, let's just go small, 3. So every element in G has order 1 or order 3. Yeah. So so here's the 3 elements that are in there.
Cool.
And one of them has got to be E. So let's actually make this E because that's an easier change. So we have these 3 things that are in there. The order of each of these elements has to be 3 because this has order 1. If either of these have order 1, then they're E again, and they're not distinct. And we're also assuming that A is not the same as B. So the order of A must be 3, and the order of B must be 3. And what that means here is that A has A to the 0, A to the 1st, and A squared. Those are the only possible things. And this B must be E, B, and B squared. But the group only has 3 things in it. Since each one of these things is distinct, they must be equal. So this is E, this must be another element in the group, and this must be another element in the group. These must be those same elements, just in a different order, possibly the same order, well, probably a different order because A and B are not equal. But there's really only possible, once you've got these right, so
A squared.
yeah. A2, and then this one probably is A1. So I don't know if that helps a little bit. A little bit? Let it sink. Let it sink. We're going to use it some today. So maybe by using it, it'll actually kind of come together. It's okay if it's not 100% registry. Let's look at corollary 4. So G is a finite group, an element A is in G, then A to the power of G, the power of the order of G is E. So let me just write this one up so we can look at it together. This is corollary 3, G is finite, A is an element of G, then A to the order of G is equal to E. Why is that without looking? What would this be? So let's go to Lagrange's theorem, or at least a corollary of it. If I have an element of a finite group, what do I know about its order? It divides the order of G, right? So that means that the order of G must equal some multiple, some integer k times the order of A. So when I take A to the power of G, power of the order of G, that's A to k times the order of A. And that's just a multiple of the order of A, so it gets you to E k different times, like essentially, right? Or you could write it like this if you wanted. That, maybe that'll even make it clear. It's just like, okay. That makes sense. Yeah, so this is like, just nuking it completely. Just that's like the highest power I could apply to it. That's a multiple of its order. Cool. Now, this next one, so beautiful. This one is completely disarming and extraordinary. This is Fermat's little, I think I need one for this. Fermat's little theorem. You've heard the name Fermat before? Yeah? No, have not? We have to talk about Fermat for just a second. So Fermat's, probably. The way I'm saying it, it sure sounds like it.
Yeah, the way you're saying it insinuates French. But
Yeah, it does. You never know. I don't think Lagrange was French. I think Lagrange was Italian.
Yeah, it sounds like
Yeah. Lagrange was French?
No.
Oh, Fermat was French. Okay.
I'll check.
Yeah, check on Lagrange. I thought he was Italian. He was European, probably. So, yeah. He was Italian.
Oh, we're nailing it.
Man. This little thing. So Fermat's last theorem is one of the greatest problems in math. It's a great story. Fermat, so we know this, that this equation, a squared plus b squared equals c squared. How many solutions are there? Integer, a, b, and c pairs to that. Can you give me one? 3, 4, 5, yeah. So these are called Pythagorean triples. What's another one? Here's a really good one to just whip out, and people are like, oh, that's, wow. Yeah, it's cool. That's a nice one, isn't it?
Yeah, that's good.
And then you can just multiply any of these by a multiple. So 6, 8, 10 is also 1. And because the squares just, the 2 times works it out. So you can just take a multiple of those. So, and there's actually infinitely many solutions. Infinitely many integral triples that will solve that. So Fermat hypothesized in his notes, this was found after his death. He was doing some work with all this stuff, and in the border of one of his problem notebooks, he wrote that a to the n plus b to the n equals c to the n has no integer solutions if n is 3 or more. So there's no triples for, so if I gave you this, you can't find 3 integers that solve that. And yeah, and then, you know, raise this even higher for any power. And then he wrote that, I have a nice proof, but it's pretty trivial, so I won't put it here, or something like that. And then this was lost, and for the next 200 years, people tried to come up with that proof and could not come up with it. This was finally proved in 1991 by a guy named Andrew Wiles, and it required math beyond my comprehension, for sure. It was just incredible mathematics to prove this.
Ben said it was trivial.
Yeah, and he said, yeah, it's amazing. So people have hypothesized that maybe he was incorrect. Maybe he thought he had it, but he didn't really have a proof.
Yeah, if it was
Yeah.
trivial.
Yeah. So Fermat's a historic figure in math. But this is Fermat's little theorem, and we do have a proof for this. So
He does get credit for this one.
yes, yeah, absolutely, 100%. So Fermat's little theorem. I don't know if Fermat called it that. Probably got called that after all this shit show
Yeah.
that he produced here, you know. That if A is an integer and P is prime, then A to the P, I'm gonna give a different version than the book, and this is the one that I think is more useful. A to the P minus 1 mod P is equal to A mod P. So we'll see, we'll do a little few examples like how incredible this result actually is. In our book, they multiply both sides, excuse me, this should this should be 1 mod P, yes. In our book, they multiply both sides by A. This is what reminded me that I had it wrong. And they have this, which I find much less useful. So do you see how you just multiply both sides by A here, and then you get this one down here?
Yeah.
Yeah? So let's do a quick proof of this, we're gonna use the division algorithm. So by the division algorithm, we can write A as some multiple of P plus a remainder. Because they're integers, so you can always just do this with any two integers. That's the division algorithm. We don't know if R is perfect or not, you know, if R is 0 or there is a non-zero remainder. So we're gonna have our cases based off of that. We do know that R will be between 0 and 1 less than P, so less than P. Because if R is equal to P, then we'll just bump M up by 1 and we have a perfect division. And we shouldn't have had a remainder to begin with. So let's do some cases. If R is equal to 0, we'll just knock that out. This means that A is just MP, so it's a multiple of P. So A mod P is what? So let's think. So if I had 50 mod 5, so here, because this,
0.
yeah, it's 0, right? So it's just a multiple of the thing I'm modding. Yeah. So this is 0. And I can raise both sides to the P minus 1th power. So if I take this, raise it to the P minus 1th, 0 to the P minus 1th, and that power just comes inside, so this literally just gets us right off the bat. It doesn't matter where you take the mod, if you do it before or after doing arithmetic with the thing, so we just get this. But this side is, this is 0, and that's the same as A mod P, so notice that that's just A mod P. Both of those things are 0 is what I'm trying to say. Anybody have a scissor on them? No, a knife?
Oh, I normally have my knife.
Yeah. I always think about bringing, I have a little nice pocket knife. I don't think we're supposed to have knives on campus.
That's why I don't bring it.
I won't
Yeah.
snitch on you.
What's that?
I won't snitch on you.
Oh, yeah. Sometimes, I mean, nobody would know. Wouldn't be the worst thing to have a knife around.
Well, everyone on YouTube knows now.
I don't have a knife. A very small shotgun in my bag.
Right.
Yeah.
Shaved off, definitely not illegal.
Exactly. Exactly. So if the remainder's 0, this is trivial because both these sides are 0. So let's assume that r is not 0. So we're going to take r between 0 and p minus 1. So what would that mean about this? So a mod p, what is that going to equal? So I'll just put this up here, so a is equal to mp plus r. It's r, right? It's just the remainder. So we got that. Does that sound good to you, Kyle? Yeah. Okay, outstanding. So this number r is equal to 1, 2, 3, on up to p minus 1. Right? It's somewhere, because we assumed that we got rid of the 0 case, so it's 1 on up to, and this should say p here, excuse me. Yes, otherwise it would go up to p minus 2. So r is one of these numbers here. Well, remember this group? What's up? It's all the things that are relatively prime to p under multiplication. What is the order of any element in here? So how about this? Let me ask this a different way. Since r is in here, so r is an element of up, this is our group, what is r to the order of up? Now, let's use some of the things we were talking, it's not on the board anymore. Yeah, it's the identity. Because this is the order of g. So remember we had that a to the order of g is e. That was one of the consequences of our big result. So this is just going to be, what's e here in this group? 1. What is the order of up? It's the order of that group. There's only p minus 1 things in there. So now we're getting, does this make sense?
Yeah.
Yeah. So we've got this. This is looking like what we're kind of shooting for. Let's go and write it out. So rewriting that, since r is a mod p, this means that a mod p to the p minus 1, because this is r, remember that, is equal to 1 mod p. And now I can just bring that power inside, so this literally just bring that inside. That's a to the p minus 1 mod p equals 1 mod p. I need to write that. It's a little more elegant to not write it. So really, really pretty easy proof, right? It's literally, but the trick is that recognizing that the possible remainders actually form up. That's the big leap that you take, and once you have that, then we just get these natural consequences. So this is the first result that I stated. And then this, if you multiply both sides by a, you get a to the p mod p equals a mod p. Like I said, that's not great. Not for me anyway. Maybe there's people that it works good for. So this result is almost essential in cryptography, where we're doing any kind of crypto. Did anybody had crypto with cyber? Has he taught that in a while? No. crypto. Yeah. Cryptography, not cryptocurrency.
Yeah, that's where my.
He's anti-crypto, so. So we just don't talk about that together. I'm super pro crypto guy. All right, so.
Are you?
Oh yeah, yeah, I love crypto. I'm pretty into crypto.
Huh, I'm not.
Yeah. I'm hoping one day. I'm hoping. I don't. Let's not. I don't, we'll some other. We'll start it. We'll waste a half hour at the beginning of a different class on that. Yeah, Monday.
Monday sounds good.
Monday sound good?
Cool.
All right, Crypto Monday. Okay, cool. So, here's some examples. If I take 2 to the 16th mod 17. So, if I asked you to do this, it would suck. You'd probably have to get a calculator. I mean, without this result, right, you'd have to multiply this out, and I think this is 65536. You'd have to do that power, and then get this, and then do division by 17 and see what your remainder was. But we know what the remainder is because of that result. So here we have P equals 2, that's our, A equals 2. P is what here? 17. And notice that this is 17 minus 1 right here.
Yep.
So this is 1.
Yep.
And that seems pretty cool, that you can just use this result to get that. And then you can check this out yourself using the actual number. So here, this is manageable. 2 to the 16th is not at all crazy. But what would be crazy is if I asked you to find 2 to the 50th mod 17. So now this doesn't quite look, this doesn't match the P minus 1 thing, right? So what we really need is like a 16 here to use that result. You need 1 less than the thing you're modding by to use it. Can you think of any ways I could somehow finagle a 16 into this?
That's equal to 2p plus 16.
Can you explain what you mean a little bit, Kyle? Sorry.
Well, I don't know. I mean, that's one way to get 16.
Oh, I see what you're saying. You're saying you're taking 2 times 17.
Yeah.
Okay, cool. That's the right way to think about this. Absolutely. So Kyle has noted that this is 2 to the 16 times, how many times 6? Actually, so I think we can make it a little cleaner, but you're on the right track. How many 16s go into 50? 3. And then what I have left over, 2, right? That's 48 plus 2.
Yeah.
So you're totally on the right track, just using the exponent laws to rewrite that. So this is actually 2, I'm gonna pull the 2 squared out front, and then this is gonna be 2 to the 16th, 3 times mod 17. And remember that, so I can pull that cubed out of there.
It's just 2 squared plus 17.
Exactly. So it's just gonna be, yeah, so let's do this, 2 to the 16th. That's 17 cubed, and then that's all still mod 17, just keeping that out there.
That's 1 and 2 squared.
And so what's this? By
1.
1. So what's our final answer?
4.
4. So I think that's kind of cool. That's like some serious computational power, no calculator required. Is this making sense? Sydney, I know you missed the proof, but does this like use of that result make sense? Awesome, let me give you one to try. Here's a good one. Here's one you're calculating. You might be able to get 2 to the 50th on your calculator. I kind of don't think you can not with great precision. You'll lose a lot of digits. So you could never do that. But here's one you definitely can't do on your calculator. Wow. Yeah, there you go. Mod 11. What What is that? You find that for me, please.
It is freezing.
It's freezing?
Freezing.
Freezing. I feel, yeah, I'm sweating.
Yeah, me too.
Yeah.
Freezing.
Do you want this? Here. Your bed. Is that better? That's literally called a blanket shirt.
They expect you to have nothing less. So I need to get a 10 out of the exponent somewhere?
Absolutely. Yep, 10 is your key. How many fingers? Yep. I eat all that. Yo, hey. Can't do it.
It's too early for candy. Can't justify it in my mind.
Well,
I had the most brutal light day I've had in a long time, so I feel.
sugar's not good because of the crash, or it's just useless calories.
It is empty calories, but yeah, I don't know. I don't know that it's necessarily a crash or any of that. I just
Not feeling it.
nah.
You're much healthier than that.
My parents made me do this like diet thing when I was younger. It's called Whole30. You just cut out all sugar for the most part, and then ever since then I've never really had.
That's awesome.
Never really had cravings or anything.
That was
so.
smart of them to do that, because most kids are just jacked up on sugar all the time.
Yeah, now I have like one Oreo and I'm like, whew, I'm good.
Only one of those.
Sugar's a powerful drug.
It's the most addictive thing I think there is on this world, to be honest with you.
I used to know some Mormon folks. Anybody here Mormon? Okay, then I can talk freely. I was gonna say, we already deleted. I'm not gonna say anything bad. I'm not gonna say anything bad. But you know, they couldn't have coffee or alcohol or anything like that. But boy, did they get the sugar going. I was just like, you're having a Coke and candy? My God.
It kind of defeats the purpose of no coffee.
Seems to. Maybe it wasn't Coke, maybe it was like a caffeine-free soda. Which is like, no, I like root beer.
Root beer fans.
Interesting.
Another thing I haven't
Good
for a very long time is soda.
What's that?
Makes one of us.
I haven't had soda in a decade.
Wow. I don't have it that often because it's
Yeah.
kind of gross, but every once in a while, like a root beer.
Personally, I'm a Dr. Pepper person.
Oh, man. Do you know the history of Dr. So, do you know the history of Dr. Pepper?
No.
It was created by a chemist trying to reproduce something he had tasted, like in a soda fountain, right? Is that right?
Like, it's like the smell of it, like he was trying to replicate the smell of
The
it
smell.
into taste, or something like that.
Yeah.
Well, you
Of
did
this
great.
very specific soda fountain in one place or whatever.
Yeah. And so then like people have come along and tried to make natural versions of it, and they can't. They're so bad. Yeah.
I love Dr. Pepper.
Yeah, it's good. My wife's a DP. Yeah, we got those little cans of it. Just
Good.
like she needs a blast of it every once in a while.
Self-control. Love that.
So do we all agree this is 5?
Nice.
Yeah.
Awesome. Good work, friends. Cool. Hey, we're doing pretty good despite all the bullshit and everything. It all worked out. Lightens our load. So we got one last thing to look at. I do want to give you an assignment.
Oh, man.
And maybe, how about this? We could just start. Here's an assignment. I want to do it before I forget. Yeah, and maybe we'll just do this last result. It's just a proof we need to go through. So it's an important proof. A lot of times we just kind of skip some things. we're gonna skip some things, for sure to even get to this. So 7, 15, 17, 24, 41, and I don't know, what do you wanna do? Sometime next week. Wednesday, let's try for Wednesday, and then you know how that can go. So it's like Wednesday, Friday, let's shoot for Wednesday.
Definitely not Monday, I'll tell you that much.
No, no, that doesn't sound good at all.
We don't have time for questions.
Question.
Exactly. We are gonna look, last thing, theorem 7.3 is the classification of groups of order 2p where p is prime.
Are you okay?
Everything okay? What's going on?
I wanna start a new page just for one theorem.
Oh, he's
It'll be a full page.
Yeah?
Yeah,
Okay.
yeah. I'll make sure it's a full page.
Damn it, Kyle.
Sorry. Well, I write pretty small, so I accept your challenge. I don't think it'll be a full page.
God, I can't even spell it. In the beginning, there was a group. No, I'm just kidding. Don't start with that.
Once upon a time.
Once upon a time, someone thought about algebra.
Abstract.
All right, so yes, exactly. Let's talk about just what does this mean, classification of groups. We actually know some things already. And we have this main result that if I have a group, so I have a group of finite order, the classification of all these is a huge problem in algebra. So like people wanted to understand every group that could possibly be. Algebraists wanted to understand that. We're okay with not understanding that probably. I know I am. Like I don't need to know that, but algebraists do need to know that. So we know already that if G is equal to P in order and P is prime, what is G isomorphic to?
Z mod P?
There you go, we just talked about that, right? So Z mod P. So if I told you, hey, I've got this group and its order is 101, there's nothing else it can be but a cyclic group of order 101. I think that's prime. Yeah. So if this is 101 and prime, then G must just equal some cyclic group where A has order, or how about this, even better, G is just isomorphic to Z 101. So if the group order is prime, you know the group, you own the group completely. You can figure out everything based upon just this simple observation here. Now we want to talk about twice a prime. So what if I had a G of order 202? What are the possible things that could be? And right now we don't know, but we're about to know. And there's really only two possible things it can be. So the punchline, let me just give you the punchline so you know what to look for. Punchline. If the order of G is equal to 2p, where p is a prime, that's really important, then G will be isomorphic to either Z mod 2p, a cyclic group of order p, or G will be isomorphic to the dihedral group of order 2p, which is dp. So a prime, all the symmetries of a regular polygon with a prime number of sides. That's what we're going to show, that has to be the case. And it's definitely good to see this once, for sure. So our proof. First off, if the group has an element of order 2p, and then the group is cyclic of order 2p. So let's just make a note here. If there exists some A in G, and the order of A is 2p, that encompasses the entire group then. All the powers of A hit everything inside the group, then G is just literally the cyclic subgroup generated by that element. I want you to think about that just for a second, because it might sound like I'm just skirting around the issues or kind of leaping prematurely here. Does that make sense to you? why that is the case. This stuff is not obvious, right? Like, this stuff is deep, and even simple things can take a while. I'm gonna erase the rest of the board while you check that out. Should a little explanation help? Okay, awesome. So if there's some element in G, so first off, I know that G has two P things in it. So it's got E, it's got some other stuff, some A1 on up to A sub 2P minus 1. And that's 2P elements right there. If one of these elements has order 2P, so let's say there's some element A in here, and that element has order 2P, then that means all the powers of A are distinct on up to A to the 2P minus 1. Does that make sense? I'm waiting for Sid. I want Sydney to believe me. Yeah. So yeah, just this thing, all these different powers are distinct, because that's what it means to have that order. So compare that to the group. There are 2P things here, there are 2P things in the group. There can't be different stuff here than there is here. So you can just like mesh these over the top of the, or mesh, I don't know, just kind of like one-to-one correspondence, these things with different elements in here. And this must be the whole group G. Does that make sense? It's just because there's nothing else these things could be but all the stuff in G. So that case is good and done. If there's an element of order 2P, then we've got the first result, then we're isomorphic to Z2P. So if this is the case, then G is isomorphic to Z2P. That's how you get that. Find one element in there of order 2P, that's your group. That's your model for this group. So let's assume there isn't an element of order 2P. And this is where the fun starts. Assume there is no element of order 2P. What are the possible element orders then? Think Lagrange's theorem and results. Yeah. What are the divisors of 2P? So 1 and P, but what else? 2. And if the thing is order 1, then that's not going to get us the group, that's just the identity. So this means all elements must have order, how about saying non-identity? Must have order 2 or P. Let's show that they can't all have order 2, so there's got to be some of order 2 and some of order P. Which is just like this, right? This is a bunch of this is a rotation, and it's flips of order 2. So that's what these dihedral groups look like. So we're headed there. So let's show they can't all be order 2. We're going to do that by contradiction. Assume they are. So every single element in here is of order 2. Let's take two different elements. Let's take A and B and G. A is not equal to B, and the order of each of those is 2. And we're going to do this for everything in there. You take any two different elements, this is true for them by this assumption that's going to blow everything up. So that means that A squared is equal to E and B squared is equal to E. But notice this also implies some neat things. Multiply both sides by A inverse, which must be in there because we have a group. So A is its own inverse, which is kind of another way to say this, right? A times A is equal. And B is its own inverse. Cool. Is this making sense so far? Yeah? Let's look at what would AB be? So A times B would equal A inverse times B inverse, because each of these is equal to their own inverse. What is this equal to inside here? If I put the inverse outside, what is inside here?
AB?
Is it AB when we do it? So like, now it's BA, right? Yeah. So BA inverse. And just think about what you'd need to multiply this by to have things kind of collapse in that way, right? So the inverse of this, or this, is equal to BA inverse, but this is just an element in the group. So it is its own inverse. Everything in this group, we're assuming, is its own inverse. Everything in this group, even products, have this property that whatever inverse is equal to itself. Because this is order 2 as well. We don't know what, but it's order 2. I'm just letting that soak for a second. So what does this mean about this group? A and B are arbitrary elements. This is true. So G is what? Wanna play hangman? There we go. Thank you. Wow. You won. Beautiful. Didn't even get the rope. All right. This is not a mathematical symbol. So G is abelian. And furthermore, I can make a nice little subgroup out of just any 2 elements. So or notice that H equals E, A, B, and then I toss in an AB. The product of these 2 things, that's actually a subgroup. It's totally closed. Can you take a minute and believe that? What would I have to convince myself of to believe that this is a subgroup of G? Well, I know, right? You'd have to make a little Cayley table, show it was closed and all that stuff. So you'd have E, A, B, A, B, and E, A, B, A, B. When all else fails and you can make a Cayley table, I mean, it definitely provides insight, right? There's nothing wrong with that. Let's do the goofy rows and columns. What goes here? Thank you. What goes here? AB, right? Just AB. We're claiming that's a different thing here. And what about, what goes here? What is A times AB? It's just B. Looking like a Cayley table, right? One occurrence of each thing. And then, ooh, what's BA? It's AB. Yep, because we already showed that. Yeah, exactly. So it's just AB, it's this thing here. What's this?
E.
E, and then what's this? A. Yep, it has to be, right? So yeah, definitely. And now we can convince ourselves of this. This A times that is just going to be B. It has to be B. That times that has got to be A, and that seems right. And then this times this is E. So that is a subgroup. And we could get a little more technical and prove to ourselves that AB is not equal to A or B. Because what would that mean actually? So if AB equaled A, what would that mean? B is the identity, and we're taking, and I should have said, assume neither of those is the identity up there, because that would have been weird and pointless too. So that would mean this, so this is definitely a distinct element. What is the order of age? Four. There's one little thing I forgot to add up here. We do assume P is greater than 2. So that's good, because what has to be true about a subgroup of a group and its order? Yeah, so the order of, so by Lagrange's theorem, the order of H must divide the order of G, which is 2p. Why is this broken? Where's the collision that just happened? Got a group of order 4. Why can't it divide 2p? Because it can't? Yeah, absolutely. I agree. Is there a less circular argument? So what are the possibilities for 2p? Let's just look at it. So like 2p, we got p, we've got 2p. So p starts where? What's the next prime? Past 2, 3. So this would be 2 times 3. What's the next one? 5. It's going to be 2 times 5. Is this ever going to be divisible by 4? No, because I'd have to have p be a multiple of 2, and that's not a prime thing. So this is impossible. Cool. So not every element can have order 2. So not every element can have order 2. I think we can finish this up. So we must have an element of order what? P. Beautiful. So we've got to have some element of order P, and that's the cyclic part of the dP. So there exists an element, let's call it A of order P. And then this A generates a cyclic subgroup of order P. And that is subgroup of the big group G. So is there stuff left over? Is there stuff outside of this group, this subgroup? We've got G. We've got our cyclic subgroup inside of here. We've got E, A, up to A to the P minus 1. How many elements are there? Or P with the E, but yeah, you're right, yeah, outside of the identity. So there's P things here. How many are total in the whole group? 2P, so there's stuff here. Let's take something outside of that cyclic subgroup, because this is half the group, right? This here is half the group. So take a B that is in G minus that cyclic subgroup. So I'm going to take B over here. What does the order of B have to be? Two or P, yeah. 2 or P. There's really only 2 possibilities. Take B, and this already includes the identity, so B can't be the identity. So 2 or P, we don't even have 1 as an option. Let's assume that the order of B is equal to B. So there's like a whole other cyclic subgroup apparently, or something. We're assuming that there's like E and B and powers of B all the way up, and that's the other half of the group. Is that possible? Well, it's not gonna be possible. I gotta look at my notes on this. All right, so, what is this?
Intersection?
Yeah, yes, exactly. And what would it need to be here? Because B is outside of that, B is not in here. Pretty close. What did they both have what in them? E. So the only thing they can share in common is E. Because if this one shares anything from here, then it just turns into this thing over here. So this has got to be E. And so the order of that intersection is 1. And now we need to look at a theorem we didn't really talk about. It's theorem, I think 7.2. Yeah, theorem 7.2. I'll just put it up here. Theorem 7.2 says that if H and K are subgroups of a group G, a finite order, then the size of all the products, this is you take everything from H times everything from K, that may or may not be a subgroup. It's only a subgroup if this is equal to KH. It's kind of like you've got a billionness to it. That this is equal to the order of H times the order of K over the order of their intersection. So we're going to use that down here. So let's take a look. So by theorem 7.2, so but by, when you hear but, you know a contradiction's coming generally in math, right? By theorem 7.2, the order of everything in A times everything in B, take all the products of all these different things, must equal the order of A times the order of B over the order of their intersection. And that's 1. So this is 1. Each of these has order P. Does that sound right? Yeah? So this is equal to P squared, the order of all products from here to there. What is the order of G? 2P. We got that, right? We keep coming back to that. So, but the order of G is equal to 2P. Think about this for a second. If I had this, and I take any two things here, take a cross product across these two cyclic groups, that still has to be in G. So like no matter what I do, if I take two things in G, it's still in G. Does that make sense? So this thing here, all these products, can't produce more than is in G. But we know that P is equal to 3 and more. So this thing is equal to like 3 squared or 5 squared. Shit, yeah. 5 squared or whatever. This is just 2 times that prime. So this would mean that P squared would have to be greater than 2P. That's the truth of the matter, but this result says that, let's see, wait. So the order of this is less than P squared. Wait, hold on. I had this. This is pretty easy, and I don't know why I'm like, it's escaping me. So we got that, this. Oh, yeah, so here's the contradiction. This thing has P squared different things in it. The order of these pairs of products, there's P squared of those. If our assumption was true that this is the case, but that would mean there's more stuff here than exists in G.
Right.
So that's the contradiction. And that means that this can't be the case. So if I take an element outside of that original cyclic group, it has to have order 2. And I think I'm just gonna, and I would ask you, because we're out of time, if you could just finish the proof, and we'll talk about it when we get back together. There's not much, there's just the home stretch, but it's gonna take a little more time than we have. And Sydney's like packed up, she's out, she's done. So now, I just wanna put this up here and then say, so order B must be 2, so please read proof, read rest. You're home, you're almost home. It'll probably make a lot of sense. I think we walked through the sticky wickets together. And then I will have all your stuff stapled together in my box on Friday, if you want it. Cool. Does that sound okay? Awesome. Thank you, friends. It was a fun day.
Thanks for the jacket, Dr. King.
Oh, you're welcome. I'm glad it helped. I think it made you a little sleepy. I think it was better maybe when you were cold, but
It could just be the 5 hours of sleep.
it's not the algebra though.
No, God, no. No, absolutely not. Could never be that. Dr.
Couldn't
King.
be that. Bye.
Bye.